Hello and welcome to the 7th video of the M2 chapter Centers of Mass. On the screen is a starter question that is a little bit more challenging than usual. If you've got time to give this a go, pause the video now. The lamina shown is a quarter circle with radius 40 centimeters and a mass of 0.5 kilograms. A mass of m kilograms is attached to the lamina at A. Okay, put that on. And the lamina is freely suspended from the midpoint of AB. Okay, put that on as well. Obviously this is 20 centimeters on either side. Find the value of m needed to make the lamina hang with AB horizontal. Well, if AB is horizontal, then the vertical is going parallel with BC down here. And the center of mass must be somewhere along this line. Now we know the center of mass of a quarter circle is, let's say, here. Call that G. And we can calculate that using the formula 2r sine alpha over 3 alpha, where in this case alpha is pi by 4. So that's 2 times 40 times sine of pi by 4, which is root 2 over 2, divided by 3 times pi by 4. 160 root 2 over 3 pi, if I keep it in exact form for now. And then what I'm going to do is I'm going to take that distance and this angle here, which I know is pi by 4, and do BG times the cosine of pi by 4 to give the distance from B to here. And that distance, if I call this D, BD is equal to BG times the cosine of pi by 4, which is 16.97 dot dot dot. And the reason I'm going to do that is because if you turn your head sideways so that this is vertical, then the m 20 centimeters here acting this way vertically downwards, and the weight of the lamina about 3 centimeters this way acting vertically downwards, that's like 2 points on a line, where I need the center of mass to be here in the middle at 20 centimeters. So I'm going to take moments about this point here. So I've got about 3 centimeters times the weight of the lamina, which is 0.5 kilograms. And the other direction, I've got 20 centimeters times m, and they need to balance in order for the center of mass of the full thing to be here on this vertical green line. So I'm going to do 20 minus this on my calculator to keep that nicely accurate. And by this point, you've probably realized that I've made this up myself, which is why the numbers are not working out very nicely. So if we do a moments equation about the point E, the midpoint of AB, then anti-clockwise, we have 20 centimeters times m, the thing we're trying to find, and clockwise, we've got 3.023 dot 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 centimeters times the weight of the lamina, 0.5 kilograms, which gives us a very, very small number, 0.07558 dot 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 kilograms. Rounding that to 3 significant figures, a very small mass is needed on A to keep this hanging so that AB is horizontal. If you got that, very well done to you. What we're going to do in this video is work with frameworks in equilibrium. We know how to find the center of mass of a framework, and as with laminas, we need to be able to solve problems involving frameworks that are freely suspended from a point. In some of these questions, you might need to use your knowledge of statics and moments from M1, as we'll see when we come to the examples. And you might need these centers of mass ideas to solve problems in later M2 chapters, which I mentioned briefly in the previous video. We'll get to that. So we're using very similar ideas to the previous video, so we're going to jump straight into some examples here. The inverted T-shape uniform framework of weight W is shown, here it is, and it is freely suspended from D and from G by two vertical strings, so that AH is horizontal. The strings and the framework lie in the same plane. That final sentence is just a formality. It's making sure that you understand that the framework hasn't been twisted in 3 dimensions. It's all lying as you see it in a 2-dimensional plane. Find in terms of W the tensions T1 and T2. Okay, the first thing to notice about this is that it is nicely symmetrical. So the center of mass must lie somewhere along this line of symmetry here. And we know it's got a weight of W. What I'm going to do then is take moments about point G, because the distance of T2 from G is 0, so as I take moments this has no effect in my equation, and I know the line of action of W is here 3 centimeters away from G, and the line of action of T1 is here 4 centimeters away from G, so I can create a moments equation that just says 3 times W must equal 4 times T1, which gives me T1 is equal to 3/4 of the weight, whatever the weight is. To find T2, all we need to do now is resolve vertically, because this is the only downward vertical force, and these two must balance that, because it's obviously not falling or raising up, it's staying in equilibrium. So W must be equal to T1 plus T2. And of course we know T1 in terms of W. So T2 must be 1/4 of W. So we found the tension in the two strings, 3/4 W for T1 and 1/4 W for T2. Part B. The string at D breaks and the framework hangs freely in equilibrium from G. Find the angle that DE makes with the vertical when the framework comes to rest in equilibrium. Okay, for this we need to know the exact coordinates of the center of mass of the framework. So I'll work with A here as my 0, 0 point. This is the x-axis, and this is the y-axis, and I'll go around my framework taking each piece at a time and creating my equation. So we've got AB is 2 centimeters long, and the midpoint is at 0, 1. BC is 2 centimeters long, with its midpoint at 1, 2. CD is 6 centimeters long, with its midpoint at 2, 5. DE, 2 centimeters long, with its midpoint at 3, 8. EF, 6 centimeters long, with a midpoint at 4, 5. FG, 2 centimeters long, with a midpoint at 5, 2. GH, 2 centimeters long, with a midpoint at 6, 1. And finally AH, 6 centimeters long, with a midpoint at 3, 0. And all of that has to come together to equal the total length of the framework, which is 28 centimeters with x bar, y bar, which gives 84, and 88 equals 28 x bar, y bar, which then gives 3 and 22/7 for x bar and y bar. Not surprising, on the x bar we knew that it was along this line of symmetry, 3 centimeters in, but more importantly 22/7 up from AH, which puts it about here. So if it hangs freely from G and in equilibrium, the vertical must go through that center of mass point from G. The angle with DE, DE is parallel to this line here, so the angle with DE is theta here. And I think what I would do is to make this line here alternate angles, so this is also theta, and we know that this distance is 22/7 minus 2. and the distance from here to here is of course 3. So tan of theta is equal to 22 over 7 minus 2 divided by 3, which gives a fairly small angle of 20.9 degrees to 1 decimal place. And perhaps I should note, in case you're confused by this, that there is a slight typo in the textbook. Although I think the wording is as I've got it here, I think the calculation they do is as if this string had broken and it was hanging from point D. So I don't think my answer will match the answer in the textbook. I think the angle they are calculating is this one here. Continuing this into the next example, the same framework now has a mass of W as opposed to a weight. Find the location of the center of mass when a mass of 1/4 W is fixed at the point H. If I put that on now, we've got 1/4 W here, and our center of mass before was here, and that represents the mass W. And we know the position of that from A is 3/22 over 7. So we're using, in part A, a system of particles on a plane, where the first particle is the whole framework, W, mass times 3/22 over 7, and the other particle is the one attached at H, so that's 1/4 W with a position vector of 6, 0, has to equal the total mass of the system times the new center of mass, x bar, y bar. As usual, the W's cancel out. Here we get 9 over 2, 22 over 7. Which gives x bar, y bar to be 18 over 5, 88 over 35. So unsurprisingly, the center of mass has been pulled to the right and down. It is now roughly here. Part B, find the angle that DE makes with the vertical when the system is freely suspended from E. So now we're suspending from E, and the vertical comes down through the new center of mass. Although my drawing isn't great. There we go. So this is the vertical. We need to find this quite big angle here. To do that, I probably would work with the really small angle in this triangle here, because the distance of this side here is quite easy to work out. That is 8 minus 88 over 35. And the little distance in here is equal to 4 minus 18 over 5. So theta is equal to 90 minus the angle of inverse tan 4 minus 18 over 5 over 8 minus 88 over 35. Keeping the accuracy by putting all of that on my calculator gives me a final answer for theta of 85.8 degrees to 1 decimal place. So I hope you can see how similar it is with frameworks as it was with laminas. Just be careful you know which one you're working with. I also hope that is enough for you to have a go at questions from exercise 3G, and maybe I'll see you in the final video to look at some non-uniform laminas.